In any case, so indeed our final talk for this wonderful conference is Brandon, and he's going to tell us about divisors, orbit, harmonics, and DT invariants. Brandon.
All right. Thank you very much for that introduction, and thank you for the opportunity to speak here. The work I'll be talking about is joint with Markus Reinecke and Vasu Tiwari. So here's an outline. We're going to be talking about a certain algebra H called the cohomological Hall algebra. And under favorable conditions, the structure of H can be described by certain numbers. These are the Donaldson-Thomas invariants. And we're going to talk about sort of a new way to think about these DT invariants using polytopes. Okay, so quivers are going to play a huge role in our story today. So a quiver is just a graph where anything goes. It's a directed graph, loops are fine, multiple edges are fine. I'm just assuming finitely many vertices, finitely many edges. And in mathematical physics, Kontsevich and Soibelman attached a certain algebra, H, this cohomological Hall algebra, to any quiver Q. So I'm quoting directly from their paper here. I am not a physicist, but evidently the motivation was coming from string theory, right? So the idea is there are certain representations called BPS states that you want to count in string theory. They correspond to how these microscopic strings are wiggling around inside everything. And you want to use this algebra H to help you do that. So I'm going to give you guys some rough idea, I won't tell you maybe all the ingredients, about how this algebra H is constructed. So we're going to want to talk about not just quivers, but quiver representations. So what's a representation of a quiver? It consists of two pieces of data. So to every vertex, we're going to attach a vector space, which for us is always going to be a complex coordinate space, c to the something. And to every edge, directed edge, we'll associate a matrix representing a linear map between the corresponding vector spaces. So one piece of data you can associate to a representation is the dimension vector, right? So it's just the function gamma on the vertices that maps each vertex to the dimension of the vector space at that vertex. So instead of C2, I just see a 2 in this vertex. And you might think about fixing a dimension vector gamma, fixing some numbers in these circles, and looking at the moduli space of all possible representations with that dimension vector. Right? So that amounts to putting stars instead of numbers in your matrices. And this moduli space, which I'll call M gamma, is just a big affine space, right? It's c to the number of stars in this picture. So our space M gamma has some interesting symmetries. If you have a linear map between two vector spaces, we try to persuade our linear algebra students, perhaps with mixed success, that changing bases at the domain or codomain doesn't really affect that map in a material way. So M gamma carries a change of basis action of a product of general linear groups, right, acting at each vertex. And I'm going to let H gamma be the associated equivariant cohomology ring with complex coefficients. And we're going to think about H gamma in a really concrete way. So I have my quiver, I have my dimension vector, and I'm going to attach to each vertex a list of variables of length equal to the number at that vertex. So I have two x variables, a y variable, three z variables. And I'm going to identify H gamma with the polynomial ring and all the variables that you see, or more properly, the subring of that ring that's fixed by permutation within lists, right? So H gamma consists of, if you like, partially symmetric polynomials. So Kontsevich and Soibelman define the cohomological Hall algebra to be a big infinite direct sum, right? So you take the direct sum over all possible dimension vectors gamma of this space, H gamma. So this is an infinite direct sum, and each summand is itself singly graded, right, by cohomological degree. And this algebra is equipped with a certain external multiplication, and I've written some words here. It's the last talk. I'll kind of be rough. So the basic idea is if I have two representations of the same quiver, there's a natural direct sum operation on these representations to put them together. You take direct sums of vector spaces at each vertex and direct sums of matrices along each edge, right? And there's a little bit of a finagling that happens here that shifts degrees and takes basically the symmetry into account. But again, you can be very concrete about this. Sorry for the crazy formula. So if I have two partially symmetric polynomials, right, representing homogeneous elements here, their product in the Kontsevich-Soibelman cohomological Hall algebra is given as follows. You consider them in disjoint variable sets, you multiply them together, you multiply them against this crazy thing, which, remember, is again coming from this degree shift, and then you apply a shuffling operator in the symmetric group algebra that basically shuffles your two sets of variables past each other. Right? So this is the product. So big picture, starting with the quiver Q, you have a certain algebra H that's multigraded according to dimension vectors. And the basic question you have is, well, what does H look like? Can we infer properties of H from properties of Q, perhaps? And I'm not aware of a nice answer to this question in general, but if you have nice quivers, your algebra H can actually have a nice structure. So what are nice quivers? Right, so this term does not appear in our paper. I just wanted a shorthand. So we're going to call a quiver nice, and we'll only look at nice quivers from here on out. If the quiver Q is connected, if I can get from any vertex to any other by following arrows, if my quiver is symmetric, so if I have 7 arrows from I to J, I have 7 arrows from J to I, and if my quiver is somewhat loopy, so every vertex has to have at least one loop. All right, so Kontsevich and Soibelman conjectured, and Efimov later proved, a structure theorem for the algebra attached to a nice quiver. So let's say you have a nice quiver. You deform the product a little bit. I don't want to get into that. What you have for your algebra is actually a supercommutative, freely generated algebra. So it's a free object. This algebra H is freely generated by a certain multigraded subspace V. So V is this kind of infinite direct sum over dimension vectors of various pieces, V gamma. And in fact, each V gamma is itself singly graded by that cohomological degree, right? All right, so this is the Efimov theorem. This big algebra H is somehow governed by this somewhat smaller subspace V.
Excuse me, that's a question.
Right, so the question is, what do I mean by supercommutative? I mean by a commutative up to an appropriate sign. Right. All right. So Efimov's result is restated here. And we might want to record the dimension data of this generating subspace V, right? So each piece, V gamma, is finite dimensional. So if gamma is a dimension vector, the numerical Donaldson-Thomas invariant dt gamma is just the dimension of V gamma. And each V gamma is itself singly graded, so we can actually record its graded dimension, its Hilbert series. This is the quantum Donaldson-Thomas invariant. So if you take the quantum invariant, plug q equals 1 in, you get the numerical invariant. And we're going to, sort of as good combinatorialists, look for ways to compute this dt gamma q. So your first attempt might be to look at this Efimov theorem, say, H is freely generated by V, interpret that as an identity of a multigraded Hilbert series, and see what you get. And what you get is this, right? So, we have an Euler form showing up, we have a plathistic exponential, and then here in red is the thing that we want. So this is a problem informal power series, which for me at least is very scary. And it may not really be so obvious from this that these dt gammas are combinatorially interesting objects. So that's what I want to convince you of in the remainder of the talk. So this process of persuasion will take a few steps. First, let's assume you have a nice quiver and a dimension vector. I'm going to build a graph, g gamma, from this data. So the basic idea is I look at the numbers appearing in my vertices, and each number is going to give rise to a family of vertices in my graph, right? So this 2, for example, gives rise to 2 vertices over here. If it was a 7, I'd have 7 vertices. And if I have a pair of edges between distinct vertices, that's going to give rise to, well, edges with the appropriate multiplicity between each pair of vertices in the corresponding families in my graphs. And a loop at a given vertex will correspond to really a copy of the complete graph at the corresponding family, with the proviso that somehow the first loop didn't really count, right? So it's some combinatorial construction. So what am I going to do with these graphs? I'm going to consider divisors on them. So a divisor, D, on a graph G, and here I really only mean an effective divisor, is just a function which sends any vertex of G to a non-negative integer. Right? These are also sometimes called things like chit placements. The degree of a divisor D is the sum of its values, and I'm going to want to consider some special divisors called break divisors. So we've seen in a few talks already that the genus of a connected graph is the number of edges minus the number of vertices plus 1. This is the topological genus. And a divisor D on a connected graph G is a break divisor if, well, first off, its degree is equal to the genus of the graph, and furthermore, if for all connected subgraphs H of my graph, the degree of the restricted divisor is greater than or equal to the genus of H. So let's see an example. Here's a graph that's homeomorphic to the Greek letter theta. It has genus 2. And here are 2 divisors on my graph that have degree 2. Right? Sum of numbers and circles is 2. But this divisor over here is somehow bad, right? Because this red triangle, right, has genus 1, but the sum of the numbers and the circles is only 0, right? So this is not a break divisor, but it can be checked that this thing in the middle is in fact a break divisor. So again, we have our nice quiver, we have our dimension vector, we associated this graph G gamma, and I'm going to look at the corresponding set of break divisors, which I'll call Z gamma, and I'm going to interpret this set geometrically, right? So the conditions for being a break divisor consist of a whole bunch of linear inequalities and equalities. So what I have is, in fact, the integer points inside a polytope, right? So we can think about this somehow as the polytope of break divisors. In this case, it looks like an ice cream cone somehow. Officially, it's a polytope in R4, but because my break divisors have to satisfy W plus X plus Y plus Z equals 2, right, this is a 3-dimensional object. So any automorphism of a graph induces a symmetry on the set of break divisors, and we're actually only going to consider the automorphisms that come from permuting vertices within the same family. So like this 2 in my quiver gave rise to 2 vertices over here that are kind of twins. And you can think about the action of S2 that like swaps those guys, and that corresponds to chopping your ice cream cone in half along this hyperplane, right, and thinking about reflection across that hyperplane. It looks like a line because you're seeing it head on, but you know what I mean. And in general, Z gamma is going to carry an action of a product of symmetric groups corresponding to my dimension vector. So now we can state the numerical version of our main theorem. So the numerical DT invariant is just the number of S gamma orbits in this polytope, right? So in this particular case, I see 4 orbits of size 1. These are the red points. And these black points form 2 additional orbits of size 2. And therefore, the numerical DT invariant is 4 plus 2, or 6. So here's kind of an infinite family of examples. It's a really little quiver, just 1 vertex, but we have a dimension vector n. And you look at this polytope known as the trimmed permutahedron. So you take a staircase, but your staircase is just a little bit depressed. It starts at n minus 2, goes to n minus 3. Eventually, you have 1, and then 0, 0, right? You look at the integer points inside here, and you get a locus of size n to the n minus 2 that has an action of Sn. And the number of Sn orbits, i.e. the numerical invariant, is given by this formula. This is a result of Kumvalinka and Tawari, right? So we have, you know, this big sum over divisors. We have a number theoretic Möbius function. It's not obvious this is an integer. It's not obvious it's positive. Here's how it looks. 1, 1, 1, 2, 5, 13. Not everything's a Catalan number, I'm afraid. So what about the quantum case? Let's try to be a little bit more ambitious. How'd that get in there? So we're going to introduce sort of a crash course in a very powerful technique in combinatorial representation theory known as orbit harmonics. So I can't really do it justice in the time that I have remaining. But orbit harmonics is a machine. It takes in a finite locus of points, z, and in space c to the n, and spits out a graded quotient ring, R of z. And here's how it works. You start with z. You look at the ideal of polynomials that vanish on z. That's typically inhomogeneous. You take the associated graded ideal that is homogeneous. You look at the corresponding quotient of your polynomial ring at the level of, I guess, varieties or schemes, if you like. You start with these reduced points in a locus, and you sort of smash them all into the origin, and you get something of high degree, right? And this process is especially nice when your locus z has a certain symmetry. Like you could think about these lines as generating S3 by reflections. And as a matter of fact, the ring RZ that you get will inherit any linear symmetry that was in your original locus. So orbit harmonics is just absolutely everywhere. You can think about co-invariant rings, Tanasaki quotients, delta conjecture models, objects related to Coxeter-Catalan theory, a very beautiful thesis of Sean Griffin, even the Garcia-Heyman modules in terms of orbit harmonics. And always the game is you want to choose a point locus that's interesting. If you start with an interesting point locus, you might get an interesting ring. And what are some interesting point loci? Well, for polytope people, why not take the integer points inside a polytope? Right? So I actually haven't seen this show up in orbit harmonics before this project. So that was kind of interesting to me. And here's where it shows up. So let's again look at this locus of break divisors, z gamma. Let's take the associated orbit harmonics quotient. So it's a graded module over this product of symmetric groups, S gamma, corresponding to our dimension vector. And the quantum DT invariant is just the Hilbert series of the associated fixed subspace. Right? So it's the graded trivial component. And again, what might these things look like? What might these rings look like? So we'll return to our example of a quiver with one vertex and two loops and dimension vector n. So again, our locus consists of the lattice points in this trimmed permutahedron, right? And what we have is something with an action of Sn. It's a graded Sn module. So if you take this Sn module and you restrict from Sn to Sn minus 1, what you get is the action of Sn minus 1 on length n minus 1 parking functions. And what is the grading? Well, in the lingo of Macdonald theory, its area are really co-area. So here's the kind of relevant Nabla formula. So somehow the action of Sn minus 1 on size m minus 1 parking functions admits a hidden extension from Sn minus 1 to Sn that's not so obvious. And this extension shows up actually in Donaldson-Thomas theory. So a couple of suggestions. You might want to actually determine the graded S lambda structure of this ring RZ, or the graded S gamma structure, sorry, of this ring RZ gamma. Right? In particular, this would sort of extend the area grading on parking functions. And here's another suggestion for those of you who like polytopes. Take your favorite polytope P, look at the integer points inside that polytope, and try to compute this orbit harmonics quotient. See if you get something nice. And if your polytope is G stable for the action of some crystallographic group G, that's finite, then what you're actually going to get is a graded G module, and it might be interesting to look at its character. So there are various ideas showing up in the proof. I'm nearly out of time, so I will be quite quick here. What you basically do is you show that a whole bunch of things are isomorphic to one another. You take this construction of Efimov, you sort of desymmetrize it, you get a connection with bond ideals, you relate this ring RZ gamma to the power ideals that were studied by Ardila-Postnikov and Postnikov-Shapiro, and you use the results of, say, Postnikov-Shapiro or Ardila-Postnikov to look at the Macaulay inverse system that you would get. right? So it's basically this big, long chain of isomorphisms. And with that, we have come to a very somber but necessary point in every FPSAC. The last slide's incoming. Here it goes. Thank you all for listening.
All right, thanks, Brandon. Have you got questions? Yes.
Hi, thanks for the talk. I was wondering if you needed to fix a stability condition in the background, or is that not necessary?
Yes. So the question was, do you need to fix a stability condition in the background, or is that not necessary? Yes, there is a stability condition being fixed. So, yeah.
Okay, I feel like I've asked you this once before at a different conference. I'm going to try again. If you have a 3-loop quiver, there's some older technology that basically says, in some sense, Donaldson-Thomas invariance associated to dimension vector n is supposed to count plane partitions of n. Can you see this using your technology, or does this sound completely unfamiliar?
All right, so the assertion was that this question was asked of me already. I don't recall it. So I'm sorry, but the question was, if I have a 3-loop quiver, a 3-loop single vertex quiver, there should be some connection between the quantum DT invariant and the ordinary DT invariant and plane partitions of n. I am not aware of one. That sounds very interesting. The corresponding graph that you would get is sort of like the complete graph on in vertices, but you'd have 2 edges between each pair of vertices. That might be amenable to some of our technology. I'd love to talk more. Yes.
So I was curious, you sort of, this kind of went fast and I missed something, but the DT of Q gave you the Hilbert series for something, and one of your questions was like, basically, how do you get the SN permutation? Is there a way to get a symmetric function or a Frobenius out of like the quiver theory, or is it just like a Q series?
All right, so the question was sort of from the quiver setup, do we just have a Q series coming from the Donaldson-Thomas invariant, or do we get a whole Frobenius image? So we actually have a whole Frobenius image, right? This R of Z gamma carries an action of a product of symmetric groups S gamma, right? So we're kind of throwing away a lot, in a sense. We're only looking at the trivial component to get the DT invariant, but it might be interesting. I cannot assert that it would be interesting from the point of view of physics, but it might be interesting for us to look at this kind of S gamma structure.
Can you realize the polytope, thank you for pulling up this picture again, that polytope as the Newton polytope associated with some valuation?
So the question was, can I realize this polytope Z gamma as the Newton polytope associated with evaluation? I don't know.
So this break divisor stuff was introduced in the context of chip firing, if I recall correctly. Do you see the dynamics of chip firing anywhere in the stuff that you're looking at?
So the question was, break divisors were introduced and show up a lot in the context of chip firing. Do I see chip firing in this context? Not yet, but I would like to. I mean, there are many connections, right, between these break divisors and spanning trees and chip firing and so forth.
Can you write down the multiplication maps to combinatorial way in the DT algebra, right? I mean, you've got the vector space, maybe you can actually multiply it.
Right. The question was, is there some way of writing down the multiplication maps in the DT algebra given this particular vector space? Well, I guess in some sense, like these vector spaces can be thought of as a whole bunch of free generators, right? Their direct sum would be a free generating set of the DT algebra. So I could give you a very boring answer, but I don't know of a more interesting answer than that.
You're right, it was not as good. I wasn't thinking quite right. Thank you.
I have two, if you don't mind. So first, when we define the definition of a nice quiver,
why we would want to include that third restriction that every vertex has a loop?
Right. So the question was in the definition of a nice quiver, why we would want to include the restriction that every vertex has a loop. And the answer is you want the Efimov structure theorem to hold, right? You want actually this free generation so we can make meaningful sense, right, of what it means to be a DT invariant.
And then my second question was, in this, you gave the size of Vn to be n to the n minus 2. This also happens to be the number of trees that have labeled vertices. Is there any reason why those numbers would be the same?
So the question was, here it is. In this example, the size of the locus Zn is n to the n minus 2, which counts, among many other things, trees, right? Is there a reason for that? The answer is absolutely yes. So the work of various people, including Baker, Kuperberg, working on building on work of Bernardi, I'm missing some, I'm sure, give a bijection between break divisors and spanning trees, right? So there is sort of good reason for that.
All right. Maybe final question?
Brendan, in your question toward the end about the group actions on lattice polytopes, can you combine that question with Stapleton's equivariant Gerhardt theory to simultaneously for all dilations describe this orbit harmonics?
All right, that's a wonderful question, Vic. So my advisor, I was expecting it. So the question was, there's this notion of equivariant Earhart theory, which is basically counting points and dilations of polytopes up to symmetry. And is there some relationship or combination between that and the kinds of characters that we get this way? And I've looked at this. You have two different notions of G characters, and these are often just different objects, right? So I'm not sure if there's a relationship between the two or if their combination would be interesting, but I think that would be a very nice thing to explore.
Okay, maybe you've provided us with an argument to have you as the first speaker of the next conference, not the last. So first of all, it's not so easy to forget all the questions then because you're not that exhausted and there's a whole week to answer them as well. But in any case, let's thank Brandon again.